Klimkowicz-Pawlas. It is a pleasure to me to be here and to present some information regarding, I'm sorry. Some information regarding soil indicators with special focus on complexity. The first part of presentation will be focused on key physical, chemical, and selected biological indicators. And next, I will try to describe indicators proposed in the soil monitoring law and some points as a discussion of relevance of these indicators. And the last part of our presentation will be given by Grzegorz Siebielec and with special focus of the needs for flexible approaches regarding selection of soil indicators. In the literature, we can find many different soil indicators, biological, chemical, physical. It is a broad range in each group, and such indicators are also the subject of soil mission initiative. And also in the Prepsoil project, we tried to evaluate how often such indicators are used in soil monitoring. And it was found that the most important are soil organic carbon stock or soil organic carbon content, soil pollution, soil nutrients and acidity as chemical indicators, soil structure, including soil bulk density as physical, and soil biodiversity, soil biological indicators as the third group of those parameters. At the beginning, a few words about the key physical indicators. I will focus only on some of them because, as you saw on the first slide, it is a broad range in each category. And I will focus only on those which are important for implementation of this future soil monitoring law. The first one, it is soil bone density, which is very important for key soil processes and plant productivity, such as soil infiltration, availability of water, soil porosity and aeration, availability of nutrients, and also for activity of soil organisms. Soil bulk density influence also the plant growth, and in the literature we can find different ranges for bulk density as ideal range for plant growth, as extremely bad if bulk density is very high. The restriction in root growth is observed. Soil bone density is an indicator of soil compaction, and it is we should remember that when we are talking of optimal or critical limits of this indicator, we should take into account several factors like soil texture, soil particle size distribution, soil organic matter content, and also management practices. In general, well-aggregated porous soils have lower bulk density, and sand bulk density typically increases in increase of soil depth. Other important soil physical indicators are soil texture connected with soil porosity and also with water retention capacity. The key chemical indicators, the most important is soil organic matter, which the key role is in a stabilization of soil structure by binding of soil particle into stable aggregate, promoting aeration and water infiltration, in buffering crop production against water shortages by increasing soil porosity and aeration, and also by increasing water holding capacity. The role of soil organic matter is also in soil fertility by increasing nutrient cycling and storage, and also preventing nutrient leaching. And in the retention of many pollutants in soil organic matter, it is also habitat for many of soil organisms, and as a carbon sink, it is their role is also in mitigation of climate change. The key indicator of soil organic matter is a soil organic carbon content or stock. However, soil organic carbon is not a simple measurement. It's divided into different pools, and it is include also different fractions, labile or active pool, or also stable fractions. Different methods are used to measure soil organic carbon content, mainly in lab scale, from chemical oxidation through dry combustion to new spectroscopic technique as a good tool to evaluation and measurement of soil organic carbon content. The very important indicator is also soil salinity. It is accumulation of water-soluble salts in the upper part of soil profile as a result of natural and factors and human activities. Salinity increases osmotic potential of the soil water solution, so limits the plant capability to absorb water. It affects crop yields. And the good measurement of salinity is electrical conductivity. As a concentration of all soluble salts in water extracts saturated soil paste by electrical conductivity methods. And some words about key biological indicators. There are many biological, functional, and structural indicators. The most important functional indicators, the most frequently measured are enzymatic activity, microbial biomass, respiration, and carbon mineralization. The soil microorganisms play the huge range of very important functions from organic matter decomposition through nutrient cycling, chemical detoxification, and to production of bioactive compounds. The simple measurement is soil respiration, as it is measured as a release of carbon dioxide from the soil, and it is indicator overall metabolic activity of soil microbial community. Soil respiration is influenced by many factors, by substrate availability, microbial physiological state, and metabolic demands. And it can be measured by simple or more sophisticated laboratory methods. And the second key soil biological indicator is soil enzymatic activity. This picture show how microbial enzymes in soil are complex. There are many different groups of enzymes important for carbon cycle, for nitrogen cycle, sulfur or phosphorus cycle. Soil enzymatic activity, the main role is in transformation, decomposition processes, various organic substances, and soil enzymatic activity also influence carbon sequestration and nutrient cycling and availability. And how complex these structural indicators are, you can see from some graphs. Diversity of microorganisms from very small microbes to macrofauna, with and their role is in provisioning many soil ecosystem services, regulating, supporting cultural provisioning services from soil carbon sequestration through primary production, soil nutrient cycling, and to conservation on monuments. And it shows how structural indicators, biological indicators are complex. Talking about indicators, we should focus also on some criteria for their selection. And the best indicators should be sensitive to detect changes, should be easily measurable, and will allow to answer questions. And there is also important validity and reliability of such indicators. To assess whether or not soil is healthy or unhealthy, we need also some reference target or threshold values, and some frameworks for such for developing of such values were elaborated based on EGB soil results. However, we should remember that for some indicate that only reference values are available only for some indicators, and those values are sometimes different from country to country. And going to the soil monitoring law indicators, a few words at the beginning. As you know, major soil threats included in a soil monitoring law is salinization, loss of organic carbon, compaction, erosion, nutrients imbalance, contamination, sealing, acidification, and loss of soil biodiversity. And indicators included in a soil monitoring law are divided in 4 parts. Indicators with descriptors and criteria at European Union level, indicators for which some criteria should be established at member states level, and 2 parts with indicators without criteria. In a soil monitoring law, also soil health was defined as physical, chemical, and biological conditions of soil, determining its capacity to function as a vital system and to provide ecosystem services. The target as a criteria in a soil monitoring law will be the target values and also operational trigger values. The second one should reflect soil degradation levels, and target values as an ideal situation where the capacity of soils to provide ecosystem services will not decrease. And in a few words about indicators included in the soil monitoring law, at the beginning, indicator of soil salinization, electrical conductivity, And in the soil monitoring law, we have also criteria for EC value. It is a good indicator found also in the literature. Very important for soil fertility. Generally, when electrical conductivity is low, a low concentration of soluble salts is observed, and we can talk about good soil fertility. Salt accumulation in soil may take various forms, resulting in saline, sodic, and alkaline soils. And a soil is classified as saline if electrical conductivity saturation extract exceed 4 decimeters per meter. The next soil degradation process, soil organic carbon loss included in soil monitoring. And for this threat, different indicators are in soil monitoring law. Soil organic carbon concentration, soil organic carbon stock, and also soil organic carbon to clay ratio with a criteria 1 to 13. And SOC content and SOC stock are good indicators of soil organic carbon. However, we should remember that when we are talking about loss, we should measure SOC content or SOC stock in over time period, at least in 2 time period, and the better way is report as a change. Soil to clay ratio is an indicator of soil structure and stability. What about the threshold target values? There is no one universal value for soil organic carbon, and for developing such values, it should be based on a site-specific context, taking into account soil condition, climatic condition, and also land use and soil management. In the literature, there are several values as a proposal for a limit for soil organic carbon. For example, in a report soil monitoring in Europe, value 2% of stock is as threshold for this indicator. Here's some examples how these values are different depending on the soil texture and also depending on soil groups. Another example indicator is user health dashboard indicator, which suggests distance to maximum SOC level above 60%. However, this value is representing the better condition and ideal situation under permanent grassland, and is not relevant to all soil. Regarding SOC to clay ratio, it should be remembered that some authors question suitability, maybe not some indicator, but the criteria which is included in soil monitoring law. And here are some examples from France and Romania. And authors reported that taking into account such criteria 1 to 13 for this ratio, some acidic soil, for example, in France are classified as healthy, and alkaline soils often as unhealthy. So this indicator can produce some anomalies. with interpretation and with evaluation of soil quality. Soil compaction, the most important indicators included in a soil monitoring law is a bulk density with criteria for subsoil bulk density. Optional indicators included in soil monitoring law are saturated hydraulic conductivity and also air capacity with criteria given for these indicators. Air capacity depends on texture, soil aggregation, soil organic carbon content, and it is it can be found from literature that below 5% aeration and gas diffusion are insufficient for plant growth. And the second indicator, saturated hydraulic conductivity, it is sensitive parameters of soil structure and pore continuity, and thus literature said all those indicators are good for characterization of soil compaction. And based on hydraulic conductivity and air capacity, some proposed different classes for compaction, with some values as a precaution value, and with value which is also included in a soil monitoring law class 4 as an action value. Soil erosion, it is a process resulting from wearing away soil particles from top layer. The main indicator is the rate of topsoil mass in ton per hectare per year. And regarding the threshold value for this indicator, in the soil monitoring law, it should be below maximum value. This maximum value in literature reported is differed, and in some countries, for example, in Spain, three different degrees were reported. For some as a threshold value, very often 2 tons per hectare per year are given. Excess of nutrient and indicators for this threat: extractable phosphorus based on Olsen method, and as additional indicators, total nitrogen in soil, and also ratio between soil organic carbon and nitrogen. And very important is that thresholds for such indicators should be set in a local or regional context, taking into account many indicators, soil parameters like organic matter, calcium carbonate, and also types of crops and crop rotation and climate. Soil organic carbon to nitrogen ratio is an index of organic matter turnover and nitrogen availability due to mineralization and immobilization, and the value gives us information about the balance between those two processes. As ideal range for agricultural soils, range 10 to 1 is recommended as an equilibrium between organic matter decomposition and accumulation of new organics. For forest soils, in this ratio should be in a range 20 to 25. Additional indicators recommended in the literature for forest soils is also nitrogen to phosphorus ratio. And the next indicator included in a soil monitoring law, soil contamination. As an indicator, we have concentration of several heavy metals, and also concentration of selection of organic contaminants. and this is without specific threshold values for these pollutants. From the literature, we know that in different countries, there are different soil pollutants included in national legislation with special limits and target values, and even if such values exist for soil contaminants, those values are in a wide range from between countries. Only in some countries, soil properties are considered when established soil target reference values for many pollutants. How complicated is this indicator, and how it will be difficult to select which organic contaminants should be monitored? We can show from this picture, because we have a broad range of organic pollutants, from organochlorine compounds, polychlorinated biphenyls, many pesticides, and also we have a wide range of emerging pollutants. For example, PFAS, pharmaceuticals, plasticizers, or nanoplastics as such kind of compounds. Some authors reported threshold values for selected contaminants, and for example, in a user dashboard, excess of elements and values for excess of 4 elements is given as a reference. The next, it is a reduction of soil water retention and infiltration. 2 indicators were included: soil water holding capacity and saturated hydraulic conductivity. Also, retention and infiltration is included in future monitoring. However, this description of soil retention is much more complicated and much more complex than in a soil monitoring flow. In a soil monitoring flow, we have only focus on values which are caused by impact of flooding and huge rains. But the additional indicator which should be included in evaluation of this threat is also infiltration. The very important is soil acidification. For this threat, the best indicator is soil acidity. It is a common indicator widely used in monitoring of soils, and as additional indicator, also base saturation. And the critical value for pH for agricultural soils is value below 4.5, and optimal range recommended for crop production is between 5 to 7.5. I would like also to add that for forest soils, another indicator is recommended as aluminum concentration to the ratio-based cations with some thresholds. It's not included in a soil monitoring flow, but this value is from literature as the better indicator for forest soils. And loss of soil biodiversity. It is a very complex set of indicators. In the original version of soil monitoring law, we had only one parameter, the soil basal respiration, which is an indicator of soil biological activity. In a general approach published last year, we have a broad range of indicators of soil biodiversity, from metabarcoding of different groups of organisms, abundance and diversity of nematodes, earthworms, bacterial diversity based on DNA, and also as the optional indicators, set of parameters, soil biological indicators. How complex is evaluation of soil biodiversity loss? We can see from those figures, soil hosts 1/4 of living organisms on the planet. All groups of organisms are are characterized soil biodiversity. And soil biodiversity contributes to many processes which we have in a soil, to many soil functions, many ecosystem services, and groups of organisms can be divided for chemical engineers, biological regulators as micro mesofauna, or ecosystem and engineers as macrofauna. Soil biological indicators are strongly influenced by many factors, at first soil type and soil properties, organic carbon content, pH, clay content, and also climate parameters like temperature or soil draw. Land use and land management should be also included in interpretation of this kind of indicators. Determination of threshold values is a very complex task for soil biodiversity. Should be size specific and local, regional specific. And some suggestions are given regarding threshold value for biodiversity loss in a European Environmental Agency report as an unacceptable deviation from the baseline value or from the first measurement. And the last indicators including in soil monitoring flow, soil sealing and destruction. We have a broad range of given indicators without any criteria for those indicators. In the literature, the more frequently reported indicator is the sealed area per total area. And as a threshold for sealing is sometimes recommended national target to achieve no net land take. The degree of sealing and dynamics of urbanization can be assessed by different methods, from satellite images and aerial photographs through spatial planning documents, and also Corina Land cover multi-temporal maps. Soil sealing is permanent covering of soils by buildings, constructions, completely or partly impermeable. Artificial material, mostly soil sealing occurs in urban areas, leads to loss of essential soil ecosystem functions, and has impact on agricultural production, water regulation, biodiversity loss. And it's all information about the general characterization of soil indicators. And I will give you the floor to Grzegorz, who present the next part of our lecture.
Thank you, Agnieszka, for this nice overview of soil indicators. Yes, my name is Grzegorz Siebielec. I'm head of Soil Science and Environmental Analysis Department here at the Institute in Puławy. Just a couple of slides showing that sometimes we need flexible approach to when designing soil monitoring programs and the use of soil indicators. Of course, in ideal world, it would be good to analyze everything because we've got full information about soil health. We can model some relationships, but it rarely happens. With limited resources, we have to sometimes use the indicators which are the most important, or sometimes we have to reduce number of soil indicators, but to increase number of soil samples to improve resolution of soil information, or sometimes just in the specific context, a specific situation, we have to learn certain information, and this is more important than overview of all indicators we can imagine. So relevance of the use of soil indicators in a certain situation might be dependent on, for example, soil type, mineral or organic. Of course, for mineral soils, it's always good to have information, for example, for entire profile, but the key is topsoil, where plants grow and crops grow. Whereas for organic soils, which have a bit different functions, like carbon stock, like water retention for entire landscapes, it is good to know and analyze certain indicators and for the entire soil profile to 1 meter, for example. Land use type, different indicators can be in the central point of our interest for agricultural land, for urban land, for forest, or post-industrial land. The goal of soil monitoring, the specific goal might tell us about what soil indicators are the most important. If this is risk analysis, carbon stock analysis, forecast of certain degradation processes, evaluation of policies or certain practices like soil regeneration, for example. If the goal is advisory service, or if the goal of soil data collection is to feed some models, regional models, or to develop some digital services, for example. The group of indicators can be different for the region. For example, Mediterranean salinity would be more important. For mountainous will be, of course, erosion more important. Soil organic carbon would be likely important for all of regions, of course. There might be some climate or soil regional differences in terms of soil indicators to be used even within one country. For example, natural low soil organic carbon, or some regions can be more dry with lower precipitation. Next one, please, Agnieszka. Oh, thank you. This is just example what is important for monitoring of organic soils. So this is, of course, soil organic content, but also the depth of organic layer, which can be translated into stock of carbon in organic soils, or in the long term, the changes in that stock. Soil moisture is very important because this stops mineralization of peat, and the groundwater level, of course, is very important because that creates the conditions for carbon sequestration or carbon decomposition. And this map is just an example how digital terrain model versus soil organic matter content, how elevation can affect soil organic matter content in organic soils. Even difference in 30 centimeters of 50 centimeters difference in the elevation makes a huge difference in the topsoil organic matter content. Can be 8 or can be 80. And this is because of groundwater level difference. So the carbon content in the top layer of organic soils does not give any complex information for us. This is just an example of that. Next one, please. And the land use type, of course, would affect the relevance of soil indicators. For agriculture, there would be nutrients, of course, soil organic carbon, pH, salinity, any parameters that can affect general soil health and conditions of crop growth in urban areas, in urban soils. Most important can be parameters that can be translated into conditions for living, for human, or important for spatial planning. So we can, having this information, we can, for example, avoid soil sealing or land take of most functional soils in that area. So texture is important, compaction is important because soil moisture is important, and soil water holding capacity is important because moisture in soil can counteract or mitigate heat waves and temperature extremes in urban areas. In forest, carbon stock would be important, or reduction of erodibility, for example. In post-industrial areas, the most important are quite often risk monitoring. So we have to measure total contaminants, but not only solubility of contaminants, bioavailability, and those parameters that affect bioavailability of contaminants. Next one, please. For example, in urban soils, very important are soil properties that affect temperatures. We show here an example from our studies that in a summer period, the difference in temperatures measured can be quite high, 5, 6, 7 degrees at the same moment, and this depends on the properties of soil. Of course, land use type of plant cover, but also texture, organic carbon, compaction, sealing, and the quality of soil profile. If this is natural profile or some wastes are buried in the soil profile, that affects the potential of soil to mitigate soil air temperatures in summer period. Next one, please. And of course, for post-industrial soils or all soils with elevated levels of contaminants, it is very important to measure solubility of contaminants, bioavailability, depending on what contaminants is of our interest. And we show here how important, for example, for bioavailability or solubility of heavy metals is origin of soils, origin of contamination. And this solubility, which can be translated into risk, into the transfer of metals to plants, or impact on living organisms, can be can be from, like here for cadmium, from 0.05% of total content to 4.5. And this is, for example, dependent on origin of contaminants. This is parent rock material, or this is quite recent spill of contaminants or smelter dusts, for example. Next one, please. And the goal of soil monitoring, of course, affects the number or selection of soil parameters. If this is risk analysis, like for contaminated areas, stock analysis for carbon, forecast, for example, we want to build monitoring of desertification risk. So we have to select parameters that can be used to model the risk of desertification. If you want to evaluate policy or practice effects, like carbon farming effects, for example, or we want to develop a good soil advisory service for farmers, for example. So they are interested in some soil health indexes, easy to understand, and information, so they can quickly react and to improve soil. And of course, quick, cheap, and simple parameters. Or if the goal of soil monitoring is to fit some regional models, so we have to take care about parameters that go into model, but also parameters that can explain or predict the parameters of interest. Or we are also developing some digital services to combine, for example, remote data with classical soil sampling information, for example, to improve resolution of spatial information. Next one, please. Oh, and of course,
sorry to interrupt, Gregor. We have about
just
3 minutes remaining.
Just final comment.
Thank you.
This is just example of synergy between projects, and better understanding and justified use of indicators. It would be through improved and innovative soil advisory services. So I just invite you to go into NB Soil project. We coordinate this project, and this is to develop learning program for soil advisory services, and we highly rely also on other projects like Prepsoil to include the indicators in the advisory process. So thank you for this. Yes, we can go through next one and next. Yeah, and so we would invite you to have some questions and maybe comments. These are just examples of information that could be important for us. Thank you.
Thank you very much to both of you for this very